Okay, so this is going to be the video for Honors Math 3, Unit 10, Objective 3. So this is the second half. So there is already a video out for 3A, so this is just finishing up that Objective 3. So just more of the polar graphing, so some new graphing, and then also some review graphing. So the two types of graphing that we're going to be looking at are graphing circles and then a second version of limacons, so limacon version 2, but I'll always refer to it as the kidney graph. So those are the two styles of graphing we're going to cover today that are new, and then we'll have a couple of review one as well. So let's get started. Okay, so for our circle graphs, so really a circle graph, the way we want to think about that is it is more of a single petal. So if you look here, those equations are very similar to our petal graphs, and so we have that coefficient here, but the coefficient of our theta is going to be equal to 1, okay? And so that will give us really kind of a single petal graph is the way we look at it. And then the other style of circle that we'll have is just if the radius is equal to a certain value. Okay, so the same thing as what we've done previously is our orientation of our circle, meaning what quadrants is it going to cover, is just like it is for our petal graphs, our limacon graphs as well. So are you adding or subtracting a sine or a cosine? So that's what we're looking at, right? So if we have a positive sign, if we have a negative sign, that's going to determine that it will be, up in quadrants 1 and 2 or 3 and 4. Whereas if we were to have a cosine graph, then a positive or a negative cosine, so a positive would be over here in 1 and 4, whereas a negative would be over here in 2 and 3, okay? And so then the other thing that we take a look at is our value for A. So if we look at this A value right here, so our coefficient, that will tell us the diameter. So A would be the diameter of the circle, so just like it is the length of the petal, it is also the length of the circle, but in particular the diameter of the circle. And then one edge on the pole, meaning that the pole point will be always a part of the circle. Now versus if we have R is equal to B, so if it was this situation right here, so R is equal to B, then B is the radius of the circle, and then your center is the pole. So for example, if we had something like R equals 2, that graph would go out, so I'm just going to do a couple of circle here. So like if this was our grid, right? So I'm not graphing R equals 2, I'm just kind of marking my grid there. So if I were to look at R equals 2, then I would go out to that second marking, right? So I would go out, here's my first circle, here's my second circle. So anything that lands on this right here, R equals 2, that would be what my graph would look like. And so I probably did kind of reverse where I should have done the pencil for the grid mark. And so now I'm just going to kind of best I can there. Okay, so that would be my graph for R is equal to 2. Again, where the center of the pole, or the center of the circle would be the pole, so the origin here. And then it's just a circle that goes around it, out 2 circles for a radius of 2. Okay? All right, and then limacon version 2 will cover that, but first I want to go ahead and do the circle graphs here. So we're going to jump around a little bit here, and so let's go ahead and take a look at those circle equations. So I'm going to come back to the limacons, or the kidneys, but let's do the circle graphs first. Okay? All right, so for this one right here, so we have R is equal to 4 sine theta. So the first one here, we're going to go ahead and fill in that table of values and sketch the graph, and then indicate our start and our stop. Okay, so for sine of theta, so I'm just going to go ahead and evaluate each of these at theta equals 0, pi over 2, and so on. Okay, and so I'm going to go ahead and do that on this side right here. So we'll start with at theta equals 0. So I'm going to replace theta with 0, so that would be 4 sine of 0. And then I know that the sine of 0 is 0, so that would be 4 times 0, which is just 0. So at that value, so theta equals 0, the radius is 0, so that would be the pole right there. And then I would do at pi over 2 as well, so at theta equals pi over 2. And then I'll replace theta with pi over 2. So that would be 4 sine of pi over 2. Whoops, started to write a 4 there. So then that would be 4, and then the sine of pi over 2 is 1. So I really need to know those quadrantal values. So 4 times 1 is 4. So at pi over 2, I have a radius of 4. So 1, 2, 3, 4. And then I'll evaluate at theta equals pi. So replace theta with pi. And then the sine of pi is 0, so 4 times 0 would be 0. So also would go through the pole. So it's just over here at pi with a radius of 0 would be back at the pole. And so then we're going to do 3 pi over 2 as well. So that would be 4 times the sine of 3 pi over 2. And then the sine of 3 pi over 2 is negative 1, so that would just be negative 4. So at 3 pi over 2, that would be a value of negative 4. So 3 pi over 2 is here. So normally, if whatever our radius is, we would go towards 3 pi over 2, right? But because it's negative, that means we're going to go away from it, right? We're going to go on the opposite side. So then that would go from 3 pi over 2, negative 4, so going backward. So 1, 2, 3, 4, that would be that same dot. And then I know 2 pi and 0 are giving that same location point, our start, our stop, so that would be at 0 again. So we only have 2 points here to connect, and so we need to know, okay, I have this type of graph here, so I need to think of it kind of as a single petal, but not a teardrop shape. It's going to connect to make a circle. So whenever we have a single petal, it connects to make a circle. So then I, just as best as I can, kind of make that circle. And then there is my graph. Okay, so I filled in the table of values, I sketched the graph, and now when I indicate direction and label the start and stop. So remember that when we do this right here, we are only putting a dot with an arrow, right? So whenever we have that part of the directions, it just means when you label your start and stop, you're just going to put like a heavy dot in a certain color, and your direction should always be counterclockwise, right? Because that's the way we travel to get into a positive direction, okay? All right, so I know that my start was when theta is equal to 0. It's always when theta is equal to 0, right? So that is always at theta equals 0. Your radius can be whatever, but so in this case our radius is 0, so that would be this point right here, and then travel in a counterclockwise direction, so up towards the pi over 2. And again, this is going to be difficult to see this in color. For some reason it doesn't show up that well on the dot cam. Okay, so that would give me my first circle. So how would I do this without the table of values? So if I were to look at this, I see that I have 4 sine of theta, and that is a positive value, right? So positive. And then because it's sine, so if I think about where is sine positive, it's positive up here, right? So then that means the bulk of my graph, or in this case all of my graph, is going to be in quadrants 1 and 2. And then the 4 here is that diameter. And so if I look, so I just need to draw a circle up in quadrants 1 and 2 that have a diameter of 4. So 1, 2, 3, 4. And that's the way I can graph it as well. Okay? All right, so let's go ahead and take a look at another one. So for question number 4, so we want to do the same thing again. So for this particular one, I'm going to go ahead and do the table first at just the theta equals 0, because I need to know that kind of start point. So we'll go ahead and take a look at that. So if we look at theta is equal to 0, I would have r equals 3, and then replace theta with 0, so cosine of 0. And then I know the cosine of 0 is 1, and then 3 times 1 is 3. So for this one here, so I would go along the radius of 3 units at theta equals 0, so that would be right here, and then that is my start point, right? Okay, so without doing the table of values, so let's see if we can figure out how to graph this. So I see that I'm working with a positive cosine, right? So cosine is positive. And I know cosine is positive to the right because it's the x values, and then left to the negative. So that means my graph is going to be over here, and I know the diameter of my circle is going to be 3. So I already have that diameter in diameter point, so then I know that the other point is going to be here at the pole, and it'll be at one of these values here, right? And then I just need to make a circle that have that diameter of 3. Okay. And so then when I label my start and my stop and my direction, I know in this case, when theta was 0, the radius was 3. So this time my start point is not at the pole, it's actually out here, right? And then it goes in a counterclockwise direction towards that pi over 2. And then that would be my labeling of my start and stop. So whenever it asks for that kind of fill in that table of values, always at least do that first point. And if you think you can use the structure of the equation to finish graphing, you should do that. And if at any time you're not sure, you should definitely just plot your points. Okay? All right, and then let's go ahead and take a look at this one right here. So we are going to graph. So this is just saying that the radius is equal to 5, right? So the radius is equal to 5. So that means when theta is 0, the radius will be 5, right? So if theta was 0, the radius is 5. Well, what if theta was pi over 2? Well, it's still going to be 5. So when we write something like this, it means that it is not dependent upon theta. R will always be 5 regardless of what theta is, right? So, and that's because there's no theta in this equation. So regardless of theta, R will always be 5. So I could put in a 5 here, and it will still be 5. I could put in a -2, it'll still be 5. It doesn't matter what numbers I put in for theta, the radius is always 5. So that means at 0, the radius would be 5. At pi over 2, it's still 5. At pi, still 5. At 3 pi over 2, it's still 5. So this is that circle that we were talking about on the front page, where then it's really just kind of that ring with the center of the circle at the pole with a radius of 5. So that would be my graph there. And then labeling my start and my stop. So it would be when theta is 0, my radius is 5, so that would be at this dot right here. And then going in a counterclockwise direction towards pi over 2. And that would be the graph of that one as well. Okay? All right, so that's my circle graph. So let's go ahead and take a look at the other limacon. So limacon version 2, in particular, what we call our kidney graphs. Okay, so I'm going to stop calling it a limacon, and I'm only going to refer to it as a kidney graph. So if I look at this one right here, so I am going to follow kind of the same idea of graphing everything we've done so far. So to figure out our orientation of the graph, then we look at whether or not we have a positive or a negative cosine. And so like that's something we've already been doing, right? And so when I go to graph this, I'm still going to be following kind of those same directions. So if I look at this one right here, I see that the graph is mostly up here in quadrants 1 and 2, which is where sine is positive. So this would be some sort of positive sine graph, right? So if the orientation had been, say, over here somewhere, or like that doesn't give much of a dimple, but then I would know that, oh, this is where cosine is negative, so this would have been some sort of negative cosine graph. And then just as a reminder here, so our A value, right, which is our constant, our A value, which is our constant, is our shoulders, so that would be landing at A. So just like when we did the other one. And then our other version here, so this would be our A plus, oops, I went too far, sorry. That would be our A plus B, but again, when we look at those, we're looking at those absolute value marks. And then what's different is then for our inner loop right here, we don't have this inner loop like we did in the other. We have a kidney graph, meaning we have kind of like this little dimple guy right here. So this distance right here is our A minus B value. And again, when we look at that, we'll get, you know, kind of that negative value, meaning we go in that opposite direction. Okay. And then let's go on from there. So let's do a couple of graphs so we can see that. Oh, wait, one more thing I meant to mention. So how do we know the difference between the graph with the inner loop versus the kidney group graph, which gives us that little dimple? And this is where this part is important. So if our constant is smaller, so if our constant is smaller than our coefficient, so if A is less than B, then that gives us the graph with the inner loop. That gives us that one right here, okay, which is what we're going to call the limacon graph, okay. And then if we have A is greater than B, then that's when we get that kind of little dimple graph or kidney graph. So that's a terrible picture, but that's okay. So the inner loop, the limacon, is when A is less than B. When A is greater than B, so the constant is bigger than the coefficient, we get the kidney graph. Okay, so that's why I try to say limacon for the loop, and then kidney for this one. Okay, so limacon for the loop, and then kidney. So the way which is really kind of silly, but if you look at that less than, right, less than is like the L, and the L is to remind you, oh, it's the one with the loop. So if A is less than B, less than loop, it's the one with the loop. Okay? All right, so let's take a look at this. So limacon version 2, but again, we're going to call that the kidney because it looks like a kidney. Okay, so we have, let's go ahead and do this first one. So we're going to fill in the table values fully first, just to kind of have that practice and not lose sight of that kind of idea. All right, so we're going to start with theta equaling 0. So I'm going to go ahead and do that off to the side here. So I will have r is equal to 2 plus sine of theta, but replace theta with 0. And then I know that sine of 0 is just 0, so 2 plus 0 is 2. So when theta is 0, r is 2. And so that means my first dot, so at theta equals 0, which is right here, I'm going to go out a radius of 2. Okay. And then from there, I'm going to substitute in pi over 2. And then I know that the sine of pi over 2 is 1, so 2 plus 1 is 3. So when theta is pi over 2, r is 3. And then let's go ahead and evaluate at pi. And so I know that the sine of pi is 0, so 2 plus 0 is 2. And let me go back and plot this point here. So at pi over 2, which is up here, r is 3. And then at pi, r is 2. So I'm going to go towards pi 2 units. And then evaluate at 3 pi over 2. And then sine of 3 pi over 2 is -1, so 2 minus 1 is 1. So then at 3 pi over 2, I'm going to go towards it 1 unit, so that would be right here. And then 2 pi, of course, would be the same value, and so that would be 2. So now when I go to graph this, since I'm drawing that kidney graph, I'm going to go ahead and connect these three right here, kind of like in a roundish shape. That wasn't very good. So I usually, what I do here is I go ahead and just kind of make my little frowny guy right there, so my little frowny guy to get that dimple, and then I just kind of swoop to connect it, and then swoop to connect it. And that's how I kind of get my little kidney graph. Okay? All right, so how would I graph this? Oh, let me do my direction here first. So I know that theta equals 0, r was 2, so then that would be right here. And then go in a counterclockwise direction towards pi over 2, and then that would be the graph for that. Okay? All right, so how would I have graphed this otherwise? So I know that I have a positive sine graph, so sine is positive up here. So that would tell me the orientation, right? So that means we're going to have the graph pointed upwards in that sine direction. And then I know A is 2, so those would be my shoulders. So these were out at 2, which they were, yeah? And then 2 plus, there's an implied 1 here, so 2 plus 1 is 3, so this would go out to 3, 1, 2, 3, which it did. And then when I subtract, 2 minus 1 is 1, so then instead of going an inner loop of 1, I would go down 1 to get that kind of extra little kidney shape there. Okay? All right, so let's go ahead and take a look at this one here. So this would be a time where, like, you should be pressing pause to go ahead and try to do that. So, you know, maybe hit pause, try to fill in the table and graph it, or just try to graph it and then look to see where you're at, okay? Okay, sorry about that. I had to reply to that email, otherwise my phone was going to start ringing in the middle of the video. Okay, so here we go. So I'm going to just do the theta equals 0 first. So let's go ahead and do that. So at theta equals 0, then r equals 3 minus 2, and then cosine of theta, replace theta with 0. So that would be 3 minus 2, and then I know the cosine of 0 is 1, so 3 minus 2 is 1. So when theta was 0, r is 1, so I'm just going to put a little dot right there. And then go ahead and plug in pi over 2. And then I know that the cosine of pi over 2 is 0, so 3 minus 0 is 3. So at pi over 2, my radius would be 3. Okay. And then so on. Okay, so I'm going to stop for a minute on the tables, and then how would I graph it if I didn't know it was, or if I didn't want to do the tables. So I know that I have that negative cosine, and I know cosine is negative here. So I know my orientation is pointed leftwards, right? So it's going to be something like that with some sort of like kidney there. So then this gives me my shoulder values, right? So that means these values right here, r is equal to 3, so I'm going to go up 3, which I did already through plotting a point, but I would also go down 3, right? And then I know that when I add these two together, so 3 plus 2 is 5, that gives me the direction, how far out that way I'm going to go. So then now I'm going to go 5 units out from the pole towards the left, because it's a negative cosine graph. And then I subtract them, so 3 minus 2 is 1, so I'm going to go 1 unit out to the right, which I already did. So then I'm just going to connect this to kind of give me that rounded shape, right? And then this I always kind of make my little kind of arc there just to kind of help me get a good direction on that. And then I'm just going to kind of swoop and connect these others. So that's like my little, that's what I call a swoop, okay? And so that gives me that kind of kidney shape as well, or cardioidy kind of shape. Okay, and then let's go ahead and do my start and stop. So I knew that at theta equals 0, my radius was 1. So that was this guy right here. And then I go in a counterclockwise direction towards pi over 2. Okay? All right, so there are circles and limacons. And then let's go ahead and take a look at our linear review section. So this one was from, I believe, objective 2. It might have been objective 1. So this was like when you were converting and graphing. So these are just kind of reminders of that, just to kind of pull in some review ideas as well. Okay, so for this one here, so they want us to convert to rectangular form. So to convert to rectangular form, I need a substitution for secant, right? So I know that secant is the reciprocal of cosine, which is usually adjacent over hypotenuse, or x over r. But because we're doing secant, it's going to be r over x, right? And so that's just coming from that definition we had of cosine, right? So cosine was x over r, so then the reciprocal secant would be r over x. Okay, so in order to convert, so our first step is always to kind of replace that trig, right? So that should always be the first thing that you try to do. So I would have replacing my trig function with r over x. And then our second step is to clear the fraction. So in order for me to clear the fraction, I'm going to go ahead and multiply both sides by x, and that's just to get rid of those fractions. Right, that was our second step. So then I have x times r, and then these will cancel, is equal to a times r. And then for here, I'm going to go ahead and eliminate the r by dividing, so divide both sides by r. And so then that would be a graph of x is equal to a. So then this would be a vertical line, right? So we have a vertical line here because we would go through the x-axis at a. So through the x-axis at a. So if this was a, we'll just call this one a right here, or whatever that value is. then it would just be a vertical line, and then that would be x is equal to a. Okay. And then let's take a look at the next one here. So we have cosecant of theta. So cosecant of theta is a reciprocal of sine. And I know sine is y over r, so then cosecant of theta is that reciprocal, so r over y. So then our first step is to replace our cosecant. So we're going to take that cosecant and replace it with our ratio here. So we would have r equals a, and then replace cosecant with r over y. And then whenever we're converting, we always want to try to clear our fractions first. So then I'm going to multiply both sides by y, and then they'll cancel on this side. So I'll have yr equals ar. And then I can divide both sides by r. So then y is equal to a. And then that's a horizontal line, right? So horizontal. And so that would go to wherever y is equal to a. So I would just look to see where is y equal to a. So let's say it's right here. And then it passes through the y-axis at a, so that would be a horizontal line. Okay? All right, so there's just a little bit of review for that one there. Okay? All right, so let's take a look at question number 6. So for this one right here, so we have, so we're asked to fill in the table of values and then sketch the graph. Okay? So for this one here, so for me, for secant of theta, even though it's secant of theta, it's easier for me to think of it as like 1 over cosine, right? So that's a reciprocal. So I'm going to actually rewrite it as 4 cosine of theta, just because it's easier for me to process cosine values than it is to process secant values. Okay. So I'm going to go ahead and do my table down here. So at theta is equal to 0, I would have r equals 4 divided by cosine of 0. And I know the cosine of 0 is 1, so 4 divided by 1 would be 4. So at theta equals 0, r would be 4. And then at pi over 2, oops, I don't know why I wrote 4. So that would give me 4 cosine of pi over 2. And then I know cosine of pi over 2 is 0. And so that would give me 4 divided by 0, which would be undefined, right? So then at pi over 2, it would be undefined. And it would also be undefined at 3 pi over 2, because cosine is 0 there as well. So we couldn't divide by 0, right? We can't do that. So I know this is undefined also. Okay, and then let's go ahead and do... sorry about that, pi, so let me squeeze that guy up here. So then at theta is equal to pi, I would do r equals 4 over cosine of pi, which is -1, so r would be -4. So over here at pi, if r is -4, then that means I'm going to go not towards pi, but I'm going to go away from pi, so I'm going to head to the right actually. So from the pole, I'm going to go 4 to the right. So 1, 2, 3, 4, which is that same dot. And then of course these are the same, so 2 pi would also be 4, so that guy there. Okay, so then I only have that one dot, and so that is going to be my vertical line. So plotting that table of values is kind of tedious to do the secant theta, you know, so again, but you should have kind of that, you know, that thought there. So the other way, of course, would be just to do the substitution way. So let me just go ahead and do that off to the side here, which is what I would encourage you to do. So I would replace secant of theta with its value, right? So I know secant of theta is r over x. Multiply the x over to clear your fractions. Divide both sides by r, so you're really just graphing x is equal to 4. So if you go out to 4, and then you would just pass through the x-axis at 4. Okay? All right, and then let's go ahead and take a look at number 7. So graphing theta is equal to 5 pi over 6. So let's just get kind of our common denominators here. So I know where that's at. So this would be 0, this would be 6 pi over 6. Half of that, 3 pi over 6, And then this would be 9 pi over 6, and then 12 pi over 6. So I want to graph where theta is equal to 5 pi over 6. So that's in quadrant 2. And so that's just a radial line, right? So we're just going to go from the pole through to 5 pi over 6, which is somewhere over here. And then that's all we would be graphing, right? So this is just the radial line through the pole towards 5 pi over 6, okay? And I know, like, for when we're plotting points and trying to decipher, you know, sometimes we'll kind of extend it out to the back like that, but that is not necessary. And if you do that, certainly make sure you dot it, though, so that we understand that that is not where theta is 5 pi over 6, but if we were trying to plot points or that sort of thing. But again, I don't recommend that you do that. Just start from the pole towards 5 pi over 6, so there's no confusion on that. Okay? All right, and then let's go ahead and take a look at the last two here. So for question number 8, so they're asking you to actually convert it to rectangular before graphing it. Okay, so then I would just go ahead and replace cosecant of theta. So again, we know that cosecant of theta is the reciprocal of sine, which is y over r. So its reciprocal would be r over y. So we're going to replace cosecant with r divided by y. And then I'm going to multiply both sides by y to clear my fractions. Oops. Yeah, okay. Fix that. And then divide both sides by r. So then I'm just graphing y equals 2. So I would go along the y-axis, so this guy right here, and then up 2 units, and I want to cross through the y at 2, so then that would just be a horizontal line. Okay. And then let's take a look at one more here, last one, number 9. So we're going to replace secant of theta. So secant is a reciprocal of cosine, which is x over r. So then secant would be r over x. And then clear your fractions by multiplying both sides by x. And then divide both sides by r. And so then we would have x is equal to -3. Okay? So I would go along the x-axis, so that would be this kind of radial line of 0 pi. And then I would go to the left 3 units, so over here. And then I would pass through the x-axis at -3, which would give me that vertical line. Okay? And so that's the end of the notes for Unit 10, Objective 3B. So you should be able to do the entire assignment now for Objective 3 between the 2 notes video. Okay? And then that's it.